thanks all for coming. Thanks for being patient here. Thanks for taking your time. We're going to just spend the next 40 minutes or so identifying the benefits of deploying a volt-var management system. Volt-var management system is a big smart grid initiative, and I'm sure you all have at least heard the buzz of it, and we want to just kind of go through some of the details of it with you. So what we're trying to provide here is answers to some of the following questions. What are VARs and how do they impact the distribution system? How can energy demand be reduced by voltage reduction? What is a volt-var management system and how you can deploy it to achieve voltage reduction and VAR loss reduction? And what are the benefits of the VVMS? And then how can sensors improve that performance of a VVMS? So looking at the power system, we're trying to improve energy efficiency. Joe Hogan mentioned this. It's a big initiative. It's been an initiative for a while, and it's going to continue to be until, as an industry, we really can improve our efficiency to a point where we've met the highest requirement that we can. We're focused right now on the distribution. Volt-var management is all about the substation transformer and outward towards the customer, and how we can efficiently drive power through that portion of the power network. So distribution losses, they typically range from 3% to 9% of the generated energy is lost through the distribution. 40%, about 40% or even more of the whole losses in the whole power plant, in the power system, is lost right in the distribution. And the distribution is a complex area because that's where it breaks out to many places, so it is more challenging to manage it, but it is manageable, and that's what we're going to talk about, reducing those losses as much as we can. The source of the losses, the step-down transformers, both at the substation but also down feeder. There's losses through those in the core, no-load losses. There's the conductive resistance through the cable itself, and then there's the reactive power losses, the VARs. So what are VARs? Well, first we have to look at all the components of an AC circuit. An AC circuit has a parent power, which is VAs, called volt amperes, that is the total power. And that is a makeup of the watts, the real power, the usable power by motors and by the load, and VARs, or volt ampere reactive power, which is unusable power as a result of inductive motors. So these VARs result in a phase shift, or the inductive motors result in a phase shift of the volt and the current. And the inductive motors result in a lagging current where the current sine wave and the voltage sine wave don't arrive at the load at the same time, and the load cannot efficiently use that power as a result. The VARs are caused by many different types of equipment, but motors, AC conditioners, air conditioners are some of the sources of that, but many sources of inductive loads. The VARs impact the distribution efficiency by reducing the power factor, the watts over the VA. So the delivered power, the usable power, the power that utilities can charge, divided by the power that they have to generate in order to deliver that power. Looking at the AC power triangle is a good way to look at that. The useful power, the phase angle, which is the delta in those sine waves, results in the VARs. And a quick calculation, Pythagorean theorem, shows us that the VAs equals the square root of the watt squared plus the VAR squared. So if that phase angle is out by 45 degrees as an example, and there's a 1 watt required, there'd be 1 VAR of losses and 1.4 VA total generation required to meet that demand. So VARs from the business perspective. VARs on the feeders, they diminish your infrastructure capacity. It requires more capacity if you're driving power down there that is unusable. You want to try to avoid having to drive power through your substation transformer, through your lines, through your equipment, your downline, step-down transformers. Those are all going to be stressed more by this extra added losses as a result of these VARs. They of course just waste energy. A generation has to generate more. They result in increased peak demands, which results in demand penalties or power factor penalties. And they deform the voltage profile, and we'll get into that later, but they result in a greater drop in voltage along the feeder. So that's VARs, and VARs, just correcting VARs alone is very important and very worthwhile initiative. But in addition to that, the volt-var management system can reduce the demand by an approach called conservation voltage reduction. And that's an approach where we try to reduce the voltages to a lower limit so that we're actually reducing real power. And many of the loads are constant impedance loads, and by reducing the voltage applied to those loads, you're going to reduce the power needed to drive that load. So the limits, the regulated limits, the low limit is 114 volts, the upper limit is like I think 126, and during a conservation voltage period, which is not intended to be operational all the time, but during peak demands, utility either will, on command or by automatic detection of the load, will drive the voltage down much lower, approaching the 114 volts. But to achieve that, you have to be able to accurately measure and determine the voltage throughout your system to ensure you're not violating that regulation and going below the 114. Some loads that benefit greatly from reduced voltage, that would energy would be reduced, would be the incandescent lights, resistive water heaters, electric stovetops, but there's numerous loads that are in this constant impedance type loads. Other losses when you drop the voltage is the core loss through transformers actually gets reduced. The loss through the transformers is reduced as a result of the excitation of voltages through that. The reduction of that voltage will actually result in less losses through those. And as we see here, 1.4% of the total losses along the feeder are due to transformer losses that can be avoided. Conservation voltage reduction is most effective on residential circuits and during peak loads. For 1% voltage reduction, 1% drop in the voltage will achieve about 0.6%, 0.76% demand reduction. And that's for residential circuits. On industrials, it's less, but it's still efficient enough where by dropping the voltage 1%, it's about 0.41% voltage demand reduction. So what is a volt-var management system? A volt-var management system, it's a distribution automation system. It's a system made up of software and components along the feeders to effectively manage distribution capacitors, load tap changes, and voltage regulators. We do so, manage those so that we can optimally reduce the VAR losses and improve your power factor. We do so we can flatten the voltage and maintain voltage profiles. And we do so that we can then, as a result of being able to flatten the voltage and reduce the VARs, we can then take advantage of a conservation voltage reduction scheme. So let's look at the components of a volt-var management system. If you look at your distribution, you have your transformer, your substation transformer, and then you have lines down. I don't show the secondary transformers, but they would be dispersed along the feeders. And then you have your loads, industrial and residential loads. First important part of VAR loss reduction is capacitors. So we deploy capacitors along the feeders. So 1, 2, 4, 5, a certain number of capacitors depending on the load and the expected VAR loss. We install capacitor controllers. There are local controllers you could deploy, and they would control that local cap only, or you could deploy the capacitor controller with communications and have a central software station controlling those and coordinating the effort of those capacitors coming on at different times, as opposed to each individual capacitor controller just controlling the one cap and not being synchronized. We install sensors like the GridSync sensors at the head end of the feeder, and those sensors then allow us the ability to monitor the load flow, monitor the VARs on these feeders to determine if capacitors need to be turned on or off, and help us to know the amount of capacitors that needs to be turned on and off. We install a network of some form. Often utilities already have it, but some kind of either one-way or two-way communications. The newer communications being WiMAX or frequency hopping spread spectrum technology, but even the older technology of VHF or paging, if you have existing that, is a usable technology for one-way. Public cellular is gaining in momentum as well, and that's another opportunity. Back at the data center, we install on a server a volt-var management software. And that software is communicating to those devices out in the field. As of right now, capacitors, but also monitoring the sensors. And then we have users of that both in the data center, but outside of the data center, either at desktops of planners, of distribution engineers, and then technicians who can take them, their laptop to the field, and as they're servicing capacitors, they can actually monitor the system and verify the operation of the capacitor by operating a cap locally and seeing the effect of it at the head end of the feeder. In addition, for voltage reduction, for conservation voltage reduction, and for voltage control, load tap changes are installed at the substation transformer, and we can control that remotely by the volt-var management software and step that up and down as appropriate in order to maintain the voltage. Downline regulators are also utilized to maintain voltage on certain portions, certain sections of the feeder circuits, and we can control them remotely as well. And then, as I mentioned earlier, for conservation voltage reduction, we're really trying to push the envelope of the voltage low, and we're only doing that at high peak demand times, but we're trying to push that as low as we can. We need better sensing to make sure we're not violating that voltage. So we can put sensors, additional sensors along the poles. At each cap station, we have sensors there that we're monitoring, but in addition to that, we can put sensors on poles, and then we can utilize automatic meter reading, and at selected customers, we can utilize the information that's achieved and obtained from those meters. So typically along the feeder, maybe 4 or 5 key customers will monitor those meters and make sure that we're not violating those, but that's giving us an overall view of the whole feeder. So a volt-var management software runs a closed-loop algorithm. It's a continuous algorithm that runs. It starts by collecting the data from the devices I just showed. It evaluates the voltages that it gets from those data points. It evaluates the power factor in the VARs at those points. It determines the priority in the control opportunities, excludes any inhibits because of failures or different reasons, and it calculates the best available compensating device, whether that's a capacitor, if it's trying to control for VARs, or for small voltage changes, it may still be a capacitor, but when the system needs a large voltage change, either because we're entering or exiting conservation voltage reduction, or because too many of the capacitors are already on and we need to still drop increase the voltage to meet that demand, then we control the load tap changer. We issue a command to that device to operate, either to step the transformer or to close or trip a cap, and then we monitor that device to ensure that the operation succeeded. And that's part of a failure analysis, important to make sure that we identified the cap or LTC operated correctly. We also then monitor the head of the feeder to make sure we see the VAR effect at the head of the feeder, or the voltage effect at the head of the feeder, to make sure, A, that cap did operate, and it did operate on the correct feeder. And that's the closed loop aspect that we're talking about. And then we log that results to allow reporting at a later time for post-analysis. So the key benefits of the volt-var management system: VAR loss reduction, maintaining voltage profile, conservation voltage reduction, and then failure detection and performance analysis. Those last two are very key, and we'll get into these just quickly here. VAR losses can be minimized. As we said, install the caps. Closest to the source as you can is most effective. In Europe and some countries, every consumer actually installs capacitors right at their facility. In the US, we're not as aggressive in controlling VARs, but by the utility controlling VARs and centrally along the feeder, we're compensating for VARs for all customers. Not as efficiently as putting it right to the customer, but as close to the customer as we can get, the more efficient we'll be. Install the communications in the controllers, as I mentioned. Install centralized software, and then maintain those. A very important part of managing a volt-var management system is to maintain those capacitors, make sure that they are working effectively, the cutouts haven't blown, they haven't failed, the switches haven't failed. And then review of VAR reduction performance, and we'll get into that in just a moment, and add and relocate caps continually as loads change and as new demands occur. So here's a quick graph of showing how on a typical day, this is one feeder, and each of these red hash marks are an indication of a closed operation of a cap. The yellow line is the VARs on that feeder. And as you'll notice in the morning at about 9 a.m., the load of the system is rising and the VARs are rising. So we end up closing a cap as the VARs hit a certain threshold. We close it, the load keeps rising, the VARs keep rising, and we have to close a second cap and a third cap to meet the VARs for the system. The blue line is the MVAs, and the green line, which you can't even see here, is the MWatts, because the MVAs and MWatts are nearly equal because we are eliminating the VARs. If we didn't eliminate the VARs, you'd see the yellow graph show the same kind of increase as the blue line. It would continue to increase, and then at the end of the day, decrease. But we're avoiding those losses through the day. The power factor is in red, and you can see it's virtually a flat line at unity power factor. So maintaining voltage profile and conservation voltage reduction. As I mentioned earlier, LTC control and voltage regulators are what help us do that by maintaining and monitoring those and stepping those accordingly. And here's a scenario where we show how we enter and exit conservation voltage reduction. We're starting with a bandwidth of voltage, typically maybe 119 to 125, that we're trying to maintain along the feeder, and that's the central dash line band. And then during conservation voltage reduction, we drop it down and we maintain a tighter bandwidth of high and low voltage, this being typically 114, this typically being around 117, 118. So instead of being a wider band of control during normal operation, we drop it down and we're controlling a much tighter band. And then we exit out of conservation voltage as the load decreases. This is a quick look at the voltage drop along a feeder. Closest to the substation, you're going to see the voltage that is being put out by the substation transformer. Along the feeder, that voltage will drop, and in light load it is not as much drop because there's not as much losses, I2R losses, because the current's not that high. But without capacitors, that drop would be significant across the feeder and would approach 114 or even lower if capacitors aren't utilized effectively. By utilizing capacitors effectively, it then flattens that voltage and into a more normal range, but that allows us to drop it down for conservation voltage reduction. So we're driving much lower at the source and still achieving the minimum voltage at the destination, at the end user. Failure detection and performance analysis. Two-way capacitor controllers have been around now for several years. Prior to that, one-way controllers, we only had the ability to operate the cap. We had no feedback back from the cap. Two-way controllers provide that at a higher cost for the controller, a higher cost for the communications, but it gives us that opportunity to now measure that voltage and perform the conservation voltage reduction. It also gives us the opportunity to put current sensors at those capacitors and measure the VARs so that when we select the cap along the feeder, we can select the cap that's experiencing the most VARs. From a failure analysis perspective, when we operate a cap, now we can get a direct confirmation that that cap is operated. If that cap hasn't operated, the controller hasn't operated, that's an indication of a communication failure, a capacitor failure, or a controller failure. But then we also still monitor the head end, of course, to make sure that we're seeing the VAR change at the head end. Neutral current is a way to put a neutral current sensor on a capacitor, and that neutral current will help us detect if any individual phase has failed. For one phase failure, we'll see the neutral current rise significantly anytime we close in the bank, and then we will typically trip that bank out of circuit when you have a single phase failure. But we'll log that as an event, log that for you to report, so you can go back and look at all your caps that have single phase failures and go after those in your technician assets and resources. A VAR loss performance tool, part of the volt-VAR management system, is to monitor the performance. Installing all this hardware, installing the software is only so good. You have to be able to monitor your performance to make sure you're actually achieving your objectives. We often will provide a service to customers, to utilities, to do an analysis of their VAR losses prior to us deploying a volt VAR management system. So you can deploy, run this analysis, see your losses prior to it, determine that you have enough losses to warrant the system, which is typically the case if you don't already have some form of volt VAR management system. And then after you deploy a system, we can rerun the same report, and you can run that report using the software itself, and you can constantly be monitoring that daily, monthly, or yearly, as often as you'd like, to see the performance, and you can compare it against the results that you last reported against. By doing so, you can prioritize which feeders are experiencing the worst and the most VAR losses, and you can really focus your resources on those, whether by adding more capacitors, fixing the capacitors that are on that feeder. But you can prioritize those. Maybe only look at the top 10% every time you're analyzing it, rather than looking at all your feeders. This is one VAR loss report that we did for a fairly large utility, but they only wanted us to do an analysis of 12 feeders, and the losses were quite astonishing. For a 23,000 megawatt delivery of $19 million worth, they were losing about 7.6 megawatt at about 0.6 million, 600K for the year. These are the feeders. There's about 10 feeders there, and you can see that the largest feeder, the feeder with the least losses, the most losses, sorry, and the feeders with the least losses had the same amount of load, 20 megawatt hour, but the losses were significant because the power factor, 99.4% versus 94.5%. And that's not uncommon to have a significant number of losses on just a few feeders. Another analysis we did was for a large utility of all their circuits, hundreds of feeders, and this showed about $12 million in overall losses for the year in VAR losses, generation losses. And this is done only monthly, so you can the reports can be done a summation of all the feeders or by breaking out each individual feeder. So the major factors driving volt VAR technology, certainly dollar savings. First and foremost, energy savings that you save, deferred build out of capacity, not having to increase your amount of capacity, and eliminating those capacitor audits to ensure your capacitors are working. It improves your grid reliability so that during those peak demand periods, we're reducing your demand and less exposure to reliability issues, and reducing carbon emissions, of course. And DOE stimulus has recognized volt VAR management as a critical smart grid initiative for these purposes, and there's funding available for those. So that's my presentation. I'm going to let Steve Lindsay continue by talking a little bit about specifics in monitoring of the feeders and how it can improve volt VAR management. Steve.
Thank you, Ron. Good morning. My name is Steve Lindsay. I'm the marketing manager for the distribution components division within ABB. What I want to talk to you guys about today is kind of really dovetailing on what Ron was just talking about, and the need that we have for sensing technology all along the feeder, and by monitoring what's going on in the feeder, how we can much more accurately control the capacitors to maximize the optimization of the energy out on those lines. What we did is I'm going to present some data to you guys on different feeders and different loads, and what we're going to do is take a look at the configurations and capacitive compensation on those lines, and then with the output we're going to look at basically volt VAR optimization, power loss, and the impact of conservation voltage reduction, or as I'll kind of show you, voltage regulation, I prefer to call it, and I'll show you why when we get to some different loads on here. This is just a general breakdown of how we did the calculations on these feeders. So we have a load in the beginning, about halfway through a capacitor, and then another load somewhere else down more remote on the line. And as we do different data sets, we'll show as those loads change how that's going to impact the results on the line and the optimization that you can get on those particular feeders. So let's take a look at two different feeders, or actually the same feeder with two different configurations. In the beginning, on the top line, we have a 500 kVA load, so a pretty medium type of industrial load. Another 500 kVA medium load. On the end, a lighter load. So it might be a larger residential area or a small commercial area. And then we'll take a look at that same load, but by adding a 200 kVAR capacitor. So what we're going to do is we'll see what the impact that capacitor will have. If we look at the first one, we see our voltage profile at the top. Okay, these are all line of ground readings coming from that load. So as we start up, just about 86, 70 volts coming down towards the end of the feeder, we'll see our voltage regulation was about 0.42%. So we dropped about 0.42% down the line. And then we take a look at our power losses. We see what happens here on the first load, that first 500 kVA load. That power loss drops pretty significantly. On the second one, again, it drops again. And then that remote light load really doesn't have a lot of impact on the feeder as we see going here. But we see the power losses, 314 watts coming down, and then the capacitance at a 0.62 megavar, 600 kVAR coming down the feeder. Now let's see what happens when you have the capacitor in. If we look at our voltage profile first, you see that the voltage profile is actually going to be a lot less. It's going to dip down like it was earlier on those first two kVAR, 500 kVAR loads. But because of the capacitor, your voltage profile is really going to start skinnying out. So in the voltage regulation, we improve that by 40%. So there's a much tighter bandwidth of that voltage throughout your feeder as you go from the substation down to the end. Your power loss increases by 15%. So you actually save 15% of that power that you were losing before just by adding one 200 kVAR capacitor. And the capacitance increases by about a third, or 33%, throughout that feeder just by adding that. Okay, so that's very important to see, and the idea is that if we can continuously monitor that feeder in real time, we can actually adjust those capacitors at all times to figure out exactly what it is that we need to do on that particular line. Let's take a look at two other examples. This is more of a load that has a heavy front end load and one with a heavy back end load. So we have the two 500 kVA medium industrial loads at the beginning, a lighter load at the end, one with a light load at the beginning, but with a remote heavy load there at the end. And let's see what the difference is as we add in capacitors with this. The voltage regulation between the two is going to drop 111%. Okay, so very, very significant voltage regulation. At the amount of voltage that you have at the beginning of the substation versus the end with that heavy load at the end is really going to decrease that voltage regulation. It has a real serious, significant impact on that. The losses on power almost doubled when that load is much more remote. The reactive requirement, though, almost stayed the same because there were no capacitors on either of those two lines. Okay, so what we need to know on feeders like this is we need to know the voltage on the feeder all up and down that line to determine what we can do to make that line as efficient as possible. Let's talk about some of the conclusions that we have on feeder monitoring. The idea that is every feeder is going to be different. Every feeder will have a different load, will have different characteristics. That load is going to change dynamically. You may have a factory that runs real strong on the first shift from say 7 in the morning until 3 or 4 in the afternoon. Second shift might be maybe half the capacity, and maybe there's just a real light load on that particular factory later on a third shift. That's how my factory particularly runs right now. And so I know that that's true. The load characteristics are going to be different. This is very important too. The different kind of loads, and Ron kind of hinted around the difference between a KZ and a KP load. Okay, KZ load being a constant inductive load where you have more traditional type of machines that are running on there. So if I look at the factory that we run, where we have furnaces and heavy electricity, normal electricity, those loads are going to be pretty standard loads that utilities have been used to been dealing with for the last 30 or 40 years. But if we look at constant power loads, if we take a look at this monitor as an example, this is a kind of motor that will have a constant power, whereas if the voltage were to drop on this has a compensator that's going to increase the current in here to compensate for that, so that the picture that we see on here won't change as voltage and current levels are variable. And so the important part of that is to say that we really need to monitor the lines to see what kind of power quality and power factor in VARs we have out there, because you're going to have different characteristics in different loads. It's also going to be affected by things like weather and temperature. Hotter days are going to put increased demands and increased stresses out on the feeder. Lines on feeders it'll grow and shrink over time. You might have a factory that does very successfully where they go from running full-time on first shift to a 24/7 operation. You may have a factory that's not doing as well where they actually reduce the amount of load that's out there. So there's lots of different characteristics out on the load that really lend itself to monitoring what's going on at all times. We need to keep voltage regulation within the limits. Obviously, you guys don't want to face any regulatory fines. We want to minimize the reactive power requirement. Okay, Ron put up some very compelling numbers of the amount of savings that can happen when the reactive power is decreased and the power factor is increased, and to be able to reduce the losses. And that's what you guys as utilities are really focused on. How can I have less generation but give the same amount of power to my customers? In order to fully optimize the distribution system, we really need to know voltage all along the feeder. That lends itself to having monitors or sensors all up and down the system so that we can fully monitor this. We need to know the reactive power flow. So we need not just current and voltage, but the different characteristics of that load, such as power loss and the capacitance on the line. Rules of thumb for selecting different monitoring points. The type of ones that you would want to, the type of feeders that you would want to monitor, feeders with mixed load types. So you may have, if we look at some of those example feeder lines, okay, maybe some of those at the very beginning were very highly inductive loads, but maybe at the end they were very highly KP type loads. And so that might even change over the length of the feeder. Feeders where the data that you're getting from smart meters that might be on the side of a home is not really adding up. We might want to put more sensing in those areas. If you're implementing a conservation voltage reduction program, you'll need sensors all along that point to see what's going on the lines, especially voltage sensing, especially down at the end of the line. And any really distribution system where you want to optimize that performance. So when you have especially large commercial loads where factories really start losing a lot of money as power is lost. We have two different kinds of current and voltage sensors, and I would invite you to step over here when this is done. I can kind of show you the difference between them. But we have what's a traditional current and voltage transformer and a split core CT that installs very quickly onto the lines that gives you revenue class accuracy. So that's a 0.3% accuracy that you can get on both current and voltage. It also gives you any phase control power to run any of the electronics that'll be in the control box. We also have line post sensors, which are not quite as accurate, but still give you pretty good accuracy at 1%. They're also very easy to install. Okay, and we have some examples of those in our booth. I thank you guys for your time.